Here we go, chapter 23, inferences about means. All right, so we're going to do pretty much in this unit, unit 6, everything that we did with proportions we're going to do with means. Now they start out, as they like to, they have an example they're going to refer to all through the chapter, and in this case, people are worried that along a particular road that is called Trip Hammer Road, people drive too fast. So they set up a little gizmo to record speeds of drivers going by, and then so they collect them, and they want to find out if the average speed of the population of drivers using the road is greater than the posted speed limit, significantly greater. Just a second, I have to open up the calculator here. I'm going to stop this. So it'd be a good idea for you to get your calculator out and put these numbers in. So you may want to stop this for a second, get your numbers put into the calculator. Once you have that done, resume it, and then let's do a histogram. And we'll get into that in just a minute why we want to do a histogram, but we're going to do a second y equals, and then we'll do an enter, and then arrow down and arrow over to where the histogram icon is, and hit enter, and then zoom 9, and there we go, and we're all set. Okay, hold it. I forgot to turn it on. Okay, and enter to turn it on, and zoom 9. Okay, now this histogram doesn't look exactly like the one in the book. The bin sizes are different, obviously. There's more of them, but it's basically the same. It's symmetrical, bell-shaped. Okay. All right. Now, if the sample is random and independent, as we've said before, and not too big and not too small, so meets the preconditions, so random and independent, not too big, not too small, then the sample statistic y bar, that is the average of those numbers, has a sampling distribution approximately normal, that is mu comma sigma over the square root of n. Now we don't know what mu and sigma are, but this is the central limit theorem again. We've run into this before, the central limit theorem, and it states that all y bars will distribute normally according to the 68, 95, 99.7 rule. Okay, so distribute normally, as long as they're random independent, not too big, not too small, and the same size. Okay? So very important. So this y bar has a normal relationship to the true population mu, as long as it is random and independent. That is, it represents the population. Okay, now we'll go into the preconditions more in a bit. Okay, but first we have to deal with a problem that exists with means that we do not have with proportions. Now, the standard error for p hat is the root p hat q hat over n. So in other words, if you know p hat, if you have a p hat, you can automatically generate a q hat. Now, simply by subtracting that from 1, just as if you know p, then you know q. That is the population parameter. Now, so if you have a hypothesis test or something, you got p and then q, and you can go ahead and you can calculate, the standard deviation for p hat. Now, with y bar, we aren't able to calculate the standard deviation that way. So the standard deviation for y bar is going to equal the standard deviation of the sample, s, over the square root of n. Now, this introduces a problem, since as the sample size, as n approaches 0, the variance approaches infinity. In other words, the variance is going to get bigger and bigger. So we have more variability. Now, what does this mean? Well, let's say here's our normal model with mu and sigma over the square root of n. Okay. Now, if we are in fact distributing things based on, say, some proposed mu and s over the square root of n, because we don't know sigma, mu might be proposed in a hypothesis, but there's no way from that to derive sigma. Then, well, here's what's going to happen. As the samples get smaller, let's say the tails get fatter and the central mound gets shorter. And so that would be a somewhat small sample. So it is symmetrical and bell-shaped, but it is not normally distributed. That is, it does not follow, this distribution does not follow the 68, 95, 99.7 distribution across -3 and +3 standard deviations. And if the sample size is even smaller, the tails are even fatter and the central mound is even shorter. Okay, and then this kind of continues, you know, in the same vein, getting shorter in the middle and fatter in the tails. So that means as n decreases, approaches 0, the z's needed for significance approach, they're going to go up. Okay, so as n goes down, the number of, let's not say standard deviations, not z's. Okay. Now, there was somebody who noticed this. The first guy that noticed this, it was a statistician working for All Things. If you're looking at this video on Sunday, St. Patrick's Day, tomorrow, I'm recording this Saturday morning, then what's interesting, he worked for the Guinness Beer Company, which is consumed quite a bit in Ireland. Maybe you've never had it, or obviously you shouldn't be drinking, maybe you drink at home or whatever, but anyway, it's a bitter, dark stout that's quite popular in Ireland. Anyway, so he's working for, and so there'll be a lot of people drinking, who are allowed to drink, will be drinking Guinness on Sunday. Well, he's the guy who noticed this tendency, because he was in charge of he would take small samples of the beer and then chemically test them. He'd probably bring them into a laboratory and test their contents and everything, make sure everything was, that there was consistency. And he noticed that the results he was getting was not matching what his statistical models were predicting. They were always off. And so he's the one who said that each sample size has its own distribution, slightly different from other sample sizes. So, and then tables were developed to handle this. So now you're thinking, well, this is going to be really complicated. And this is called the t-distribution. So instead of having z-scores, now we're going to have t-scores. And they're going to vary according to the sample size. Now, you'd think, well, okay, well, this is really, well, the calculator, obviously. The calculator knows all about this and knows how to handle this. But let's see what this looks like, just briefly. Now here's this page. This is, I believe this is, let's see, Appendix G in your table, and this is the t distribution. Okay. Now, here in the middle is the number of, let's go to the bottom first. Okay. Now, if you have a sample size that's infinitely large and you want to get 95% confidence level, here's the confidence levels, then you need 1.96, you're going to need one more 0.96 standard deviations. Okay? Well, okay, so as n gets bigger, then the distribution gets more and more normal. But as n goes down, the number of standard deviations you need to cover 95% is going to increase. Why? As the sample size goes down, these tails get fatter and the mound goes down, so more and more of the percentages of the probability are in the tails. So n keeps going down. So say you have a sample size of 24, then we'll talk about this in a second. Then you need this number here, 23, because you always do n minus 1. I'll discuss that in a second. So if you wanted 95% confidence for a sample size of 24, you would need 2.069 standard deviations in order to reach it, plus or minus. And so on, going on down. And you can see as it gets down to a small, now if a sample size is 3 or 4, then you need 3.182. Now why is it n minus 1? Well, n minus 1, so the T's are ranked in what's called degrees of freedom, DF. DF equals n minus 1. Now I can give a long explanation for why it's n minus 1, but just take my word for it that it's n minus 1. There's a reason for that. Basically, very briefly, one of the data elements is locked down by the computation of the mean, and you can't. So there's at least one data element you can't change because everything is based on the mean. All right, so we have T sub df. All right, so with n equal 23 with our Tripp-Hammer road data, df equals 23 minus 1, which equals 22. So we'll go back to the table in a second, and like I said, the calculator is going to handle all this stuff, and you're going to see it's just going to be great. So here's another picture of the mounds, okay, and so on. All right, so you can read. You should look this over. And then here's a discussion of the table. And we'll get to using the calculator in a second. Okay. Now, so finding critical values and so on. We'll do a little bit of that. So you got inverse t now, and not all the calculators have inverse t or inverse norm. So we'll anyway, we're going to talk about that in a second. All right. Now we're going to do a confidence interval, and on this sample. Okay, so let's talk about the preconditions. So it's got to be random and independent. Okay, that's always the case. Now, the 10% condition. We usually don't worry about the 10% condition because the samples are usually so small. With categorical data, we get these huge samples, thousands and thousands. That's not going to happen with quantitative data. But here's the thing that's really important. The normal population assumption. Okay? In order for the T model to work, for the T distribution to work, we need a normal population. We need a approximately normal or normal enough. Nearly normal, I think is what they say. Nearly enough. Okay? Now, So that means the population is unimodal and symmetric. Now we looked at our sample, and we don't know what the population looks like. I should look at the calculator here. Okay, but we looked at our sample, and the sample is unimodal and symmetric, so it doesn't look too bad. So we can do a histogram. Now, there's one other test we can do. Well, there's a couple of things. We could do a box plot, so we could do that in a second. But let's do a normal probability plot. And let me remind you what a normal probability plot is. Normal probability plot is very important and very useful. And what does it do? Okay, well, it takes the spread of the data. It sorts the data elements from small to large, sorts data from small to large, and then computes the z-score of each data element as if the distribution was normal. Then it plots the data versus the z-score. Now, if the data is really normal, then its z-scores, the z-scores of the data will be normal. If the data is, so here's the sample. Suppose your sample is skewed like this, okay? Then, and say the mean is, I don't know, like around here somewhere, okay? Now, so you're going to have a whole bunch of data down here that's going to be kind of low, and you're going to have some extreme values down here, okay? Now, the z-scores for these outliers, these are going to be outliers, are bigger than normal estimations. Okay? So, what's your graph going to look like? Okay, so these guys, instead of making a straight line, are going to be up here like this, and the rest of the data is kind of going to go like that. You're not going to have a straight line. So, but if the z-scores of the data more or less matches the estimated z-scores, the normal ones that are estimated, you will have a straight line, and it's going to look like this, like that. Okay? So, let's see what we get with, let's take a look here. We're going to do second and y equals, and we're going to do a normal probability plot. Here, first, let me take a picture. I'm going to take a picture of this thing here. Okay. Now, let's do the normal probability plot. I'm going to arrow down. This is this guy all the way at the end here. I hit enter. And I want, okay, L1 is where my data is from, but I want the data axis to be on the y-axis. It's just a little bit easier to see. And then the z-scores, the estimated z-scores, will be on the x-axis. So I'm going to hit a zoom 9. Okay, now, let's look at the window. There's 23 data elements. So with 23 data elements, the estimated z-scores on a normal distribution would range from negative 2.4 to positive 2.4. Don't worry about this. The scale doesn't really matter. And the y min and max simply matches how the data goes in terms of the speeds. Now, if you had more data elements, the spread would be bigger in terms of the estimated z-scores. So if you had 1,000, it would be like probably negative 3.9 or something like that, and positive 3.9. But the thing is, it's going to be totally symmetric and totally normal. Okay, so let's go back and let's here. I want to look at the graph. I'll take a picture of this window because it's kind of interesting to look at. Maybe we'll want to refer back to it. I don't know. So let's look at the graph. Now, this is actually not too bad. There's some in the middle here, kind of zigzags and stuff. Okay, but by and large, you could draw a straight line through here. It looks pretty straight, okay? It looks straight enough. All right, so the data seems to follow the pattern of a normal model pretty much. I'm going to take a picture of this. Okay, and we'll put this over. Let me make this window a little bit bigger. We can go back and look at it later if we want to check that out. Okay, so by looking at the sample, the nearly normal, the normal probability plot looks pretty good, pretty straight. The histogram looks symmetrical and bell-shaped. So this data is nearly normal. It's normal enough. Okay? So we've satisfied our preconditions and we can go on. And we can say that y bar, that is the mean of this sample, has a sampling distribution approximately normal. Okay? Now, we're going to make a one sample t interval. Okay? So it's going to be y bar instead of p hat. Let's review what it would have looked like before. It would have been p hat plus or minus z star times p hat q hat over n. Okay, now it's going to be y bar plus or minus t star sub df. So in other words, we're going to have a t star, but it's going to be that goes with a sample size of 23, which is going to be degrees of freedom 22, times the standard deviation over the square root of n. Okay, now let's just real quick, we can do this on the calculator. Let's do one variable stats. Now we're going to do the whole thing on the calculator, but let's do one variable stats here. So we'll just go stat, calc, and one variable stats. All right, so y bar is 31.04. Let's just call it 31. And we're going to use s sub x, and let's call it 4.25. Okay, so y bar, here, let's take a picture. So y bar equals 31 and s equals 4.25. All right, so now we can fill in the numbers. So it will be 31 plus or minus. Now, let's get t star df. Now, let's get this from the chart, okay? Just so you know how to do this. And let's see what was the confidence level we wanted? Let's see. 90. We're going to make a 90% confidence level. Okay. So let's go to our chart. So 90% is going to be right here, and the degrees of freedom is 22. So t star sub 22, that's degrees of freedom, is 1.717. Okay, I'm just writing that down. Okay, let's double check it. 1.717 times 4.25 over the square root. Now we're not using the degrees of freedom, we're using n. Okay, so let's go to the calculator, and then we'll compare this to the book, and we'll see how, and then we'll do the whole thing in the calculator, and we'll see how we do. So let's clear this out. So we got 31 plus 1.717 times 4.25 divided by the square root of 23. Okay, so that's, let's call it 32.5. Then I'll do second and enter to get the other command up, arrow over, minus, enter, and let's call that 29.5. So the confidence interval equals 29.5 comma 32.5. Now let's take a look at the book. Okay, and let's see what they ended up with here. They got the same thing, 32.5 and 29.5. So now we will write our conclusions. We are 90% confident that the true average speed of cars on Trip Hammer Road is between 29.5 and 32.5. 90% of all similar samples. Now, this is the interpretation of the confidence interval. Now I'm interpreting the level of confidence. 90% of all similar samples yield a CI that contains the true average speed of cars on Trip Hammer Road. Okay, so that's the interpretation of the confidence interval and the interpretation of the level of confidence. All right, now let's do this all on the calculator. So we'll do it as Smart View. Okay, stat, and then we're going to go to tests, and we're going to do a one sample. We're going to do a T interval right here. Okay, now we're going to use data, and it's from L1, and the frequency is, there's no frequency, and frequency is, and then calculate. And there it is, essentially what we got. Okay, so no difference, everything's good. All right, and let's take a picture of this in case we need to look at that later on. Okay, okay, moving on. So there's the confidence interval. And here we talked about the table and finding stuff off the table and how to use, let's see, let me make this bigger and make sure we're covering all this stuff here. Okay, we just did that. All right, now, okay, now here's all the usual precautions about how you interpret it. Okay, look these over. Remember, they're all exactly the same as the precautions with interpreting proportions. Okay, here's a little thing about the normal probability plot. We talked about that. Now we're going to do we're going to get a p-value from we're going to do a one sample t-test. So we're going to calculate a t-score. So t of degrees of n minus 1, we'll call it. We have it right here, equals y bar minus mu sub 0, the null hypothesis, divided by the standard error. Notice, okay, we're using the standard, same as what we used in the confidence interval. Okay, so this is one of the big differences. Also, there's no pooling when we get into two proportions. And the standard error of y bar equals s over the square root of n. Okay? All right. So the preconditions, we've been through those. Okay? They're not any different. We've interrogated the data. So we've already done that. But you need to do all of that. Okay? Interrogate the data. That is, make a histogram, make a normal probability plot. Okay? Now, let's go in and let's do the calculation. So our null hypothesis, h sub 0, is that mu the average speed equals the speed limit, 30. Okay, well, that's a laugh. Nobody. Anyway, the alternative hypothesis is that mu is greater than 30. That's because we're worried that people are driving too fast. All right, so T sub 22. Oh, so the t-score equals, we're just going to calculate the t-score, okay, is going to equal 31 minus 30 divided by 4.25 divided by the square root of 23, which is going to equal, let's see, 1 divided by, let's do 4.25 divided by the square root of 23, close parenthesis, close parenthesis. Okay, and so we get, let's call it 1.13. Okay, now that's the t-score. Now, we want to do a t-CDF. Now we're going to put in the left-hand number 1.13, comma the right-hand number 99, and this is what we have to put in now is the degrees of freedom. It's another parameter here. Now let's draw ourselves a picture. So here's 30, and here's 31, and we're trying to find the p-value here, which is the area right here. Okay, so now there's no way to do this except on the calculator. So we do second and vars, and here's TCDF, number 6, and we'll put in 1.13, comma, 99, comma, 22, the degrees of freedom, and we get 13.1.135. Okay, now that's the p-value. Now the p-value, once you got a p-value, there's everything's the same. So alpha's, let's call alpha 0.05. Okay, so there's no you're out of the funny business now in terms of the t-value. You got a p-value, it's interpreted always the same. With a p-value 13.5 greater than alpha, we fail to reject the null. There is no evidence of speeding on Trip Hammer Road. Okay. All right. So we got everything. We got the mechanics. We got the conclusion. We got the. Now I didn't write down but they were the same as. I didn't write the presuppositions down, but they were the same as the confidence interval. So make sure you do them. Okay. Now we got a few things to go over. Okay. Let's do the test. Yeah, here we go. Let's use the calculator to do this. So hit clear, and we're going to hit stat and test, and we'll do a t-test, number 2. Okay, and we'll use our data, enter, and then down. Okay, now the null hypothesis is that it's greater than, the null hypothesis is 30, okay, and we're trying to see if it's greater than 30, greater than the null hypothesis, and we'll calculate. Okay, and my numbers are a little different. What did I get? 1.13, and a little rounding there. I'm off by a few hundredths. We'll take a picture, and then let's do the same thing, stat tests, and t-test number 2, and let's just draw the picture. Don't forget, you can always do this. You can always draw the picture. Okay, and you can see that's a lot of area under the curve, and you're going to reject that null hypothesis. All right. So, moving on, next page. Okay. Now, they talk about significance and importance. That's no, you can have a significant test, but a meaningless difference. So suppose somehow we found that 31 was significance, we got below alpha, you wouldn't care. 1 mile an hour, it's not even noticeable. I mean, everybody who drives a car or rides in a car knows that. Okay. And notice that they talk about here that 30 was in the confidence interval, so we could use a confidence interval to test. Now, how big of a sample do we need? Well, okay. How do you find a sample size? Okay. Now, we had you think finding a sample size, maybe it was kind of a pain in the neck, but it was really strictly, all you had to do was find n, because you'd be given a margin of error, and you'd be given a z-star, whatever it was going to be. So, but now you're asked to find an n, but notice that t star, the level of significance, depends on n. If you don't know n, so you're going to have two variables. So in other words, the margin of error equals t star sub df times s over the square root of n. Well, if you're trying to find n, let's suppose you're given s and you're given the margin of error. You still have two unknowns. You don't know t star df because you don't know n. I mean, they're coupled together, but you know. So what are you going to do? Before we knew that, you know what z star was. So let's say we got a 95 level of so here's what you do. You start out using z star. So they want a 95% level of confidence when the margin of error equals 8. So we use 1.96, and they're telling you that the mean is 10 over the square root of n. So you solve this. So the square root of n equals 1.96 times 10 divided by 8. So n equals 1.96 times 10 divided by 8 squared. So let's just do that in the calculator. And so let's clear this. So we got 1.96 times 10 divided by 8, close parenthesis, square it. What did I do wrong? 1.96. I got an extra. Here, I'm just going to clear and start over again. 1.96 times 10 divided by 8, close parenthesis, squared. Okay, so that is approximately equal to 6. All right, so I go to my table, okay, and I look at, now, what degrees of freedom go with 6 for a 95% confidence interval? That's in the middle here. Well, that would be 2.571. So t star sub 5, t star sub 5 for 95% is 2.571. All right, so now I'm going to say 8 equals 2.571 times 10 over the square root of n. Okay, and so now I'm going to say n equals 2.571 times 10 divided by 8 squared. And so we'll call that, since it's a little bit over, we'll call it approximately 11. So you need 11 people to have a margin of error of 8 with a standard deviation of 10 and a 95% confidence interval. All right, back to the book. So, degrees of freedom, there's an explanation. You can get into that if you want. I'm not going to go into that now. I don't know if you're going to remember it or whatever. Just the main thing is how to calculate it. Okay, don't confuse proportions and means. Okay, you just got to be aware. And one of the things we're going to start doing is every time we run a test, we're going to name what we're doing. We're going to name the test. I've been deficient in making you do that. Beware of multimodality. Multimodality means you've got more than one population dealing with at a time. Beware of skewed data. Okay, maybe you can't, if the data is too skewed, you can't use a t-distribution on it. Set outliers aside. If you got outliers, then you do the work with them and without them. Watch out for biases. Make sure your data is independent, randomized. Interpret your confidence interval correctly. Watch out for stuff. Now, all of this stuff connects back to the first unit, and they talk about this here. And we did all this stuff way, back in the first semester, really in the first quarter of the class. So you're just drawing on skills that you already had. So what have we learned? How to create confidence intervals and hypotheses about proportions. You've learned that. Now you can do it for means, and the logic is all the same. Nothing's different. But because means are different than proportions, you've got a few different maneuvers. Okay, we're doing inference. We're learning about a population from a sample. We've learned the sampling distribution, the standard error, how to make a margin of error, and make a hypothesis. Okay, so this is the reasoning of inference. And it's very important that we satisfy the preconditions before we proceed. So the terms: the t-distribution, degrees of freedom, one sample t-interval, one sample t-test. Now, when you're doing a test, you're doing an interval or a test. From now on, we're going to name what we're doing. One sample p-interval, two sample p-interval, one sample t-test, and so on. Okay, and here's the skills that you've learned. You've got to master by starting on the homework. Do as many of these homework problems as you can. And now, a couple of things you want to be aware of is how the stuff comes out on a computer. So you need to study this. Why? Well, when you use software on a computer, it's going to produce output that looks like this. And so you want to know what you're looking at. The null hypothesis, the alternative hypothesis, the p-value, okay, and so on. So you can interpret stuff. And here's the exact same stuff we were just working on in a different format. So you want to study this explanation here. And here. Okay, you can get it in a table. Okay, study this and how the data comes out. Okay, here's the t-statistic. Okay, they give you an interval. Here you got an alpha level. Okay, so look it over. Make sure you can identify this, and then they've got the p-values here. Here's the p-value, and so on. All right. Okay. Start on the homework problems. And that's about it. And for homework, numbers 34 and 35, you should be able to do, since this went through the entire chapter. And that is it. Have those ready on Monday.